So welcome back to Physics of Music. Last time we were talking about basically predicting frequencies for stretch-stringed instruments and for instruments based on vibrations of air inside a tube. And we talked about how if you have a stretched string, then the natural vibration frequencies come from standing waves where the wavelengths are twice the length of the string, and anything that you get by dividing that by a whole number. And then similarly, for an open-closed tube, then the natural frequencies of vibrations come from standing waves where the wavelengths are 4 times the length of the tube, or that divided by any odd number. And then using those wavelengths, we can predict what the frequencies are using this basic formula relating frequency, wave speed, and wavelength. For the tube instruments, the speed that we want to use is the speed of sound, because the oscillation inside the instrument is just a standing wave in air. So it's just a sound wave. Whereas for the stretched string instruments, we have to actually predict what the wave speed is separately. And we talked about last time how the wave speed depends on the tension of that string, which is the force pulling on either side, and then also the mass per length on the string. Okay, so if you make the string more tight, then you get a faster wave speed. If you make the mass density less, then you get a faster wave speed. And in order to get the units to work out, it turned out that we had to take the ratio of these two quantities and take the square root. And in the end, this actually gives us exactly the right formula for the wave speed on a stretched string. And so then we talked about how normally varying the tension and varying the mass density is just something that you do when you're setting up the instrument. You tune your guitar or your violin using the tuning pegs to set the tension right in order to play the notes that you want. Similarly, on a piano, you tune the piano by turning the tuning knobs for all the various strings, and then you play it. But I was saying that there are various examples of musical instruments where you actually change the tension during the time that you're playing. And so one example I showed you last time is where you bend a note on the guitar. So just using your fingers, pressing the strings up higher or lower makes the string more tight. There's a greater tension force, and so then that note gets higher, so the frequency goes up. On an electric guitar, there's an accessory that is sometimes called a whammy bar that basically, again, it just changes the tension of your strings, and so it allows you to adjust the frequency of the note. I'm going to show you an example of that from YouTube, and then similarly, I'm going to show you an example of another instrument called a pedal steel guitar, where you have these pedals that, again, change the frequency of the note by changing the tension of the strings while you're playing the instrument. Okay, so let's have a look at those two instruments, starting with the pedal steel guitar.
And here is your bridge, which is also called the changer. You'll notice also, like these individual rollers, you've got individual components here. And what they do is roll with the effect of the pedal, activated by the pedals of the knee levers, and they will either release the tension or increase the tension on a given string or pair of strings, or even sometimes as many as 3 strings. In fact, sometimes they will lower one string and raise another. The pedals can allow you to play a chord, this E chord, and then when you hit the pedals, suddenly it becomes an A chord. There's a universe of possibilities depending on what the individual pedals, knee levers do, and which combination of strings you hit, and where on the neck you're situated. And that's the basics of a pedal steel guitar.
Jimi Hendrix took the bar to whole new places. He would do a lot of stuff with feedback and harmonics. So an example of that is if we take the natural harmonics, say on the 7th fret, I can play with the bar and it's going to make a really cool sound. Check it out.
Okay, so that was a couple of examples based on Western instruments. And I wanted to show you one more example based on a Chinese instrument. So this is called the guzheng, and it's an ancient, so like 2,000 years old stringed instrument where you see that the strings are raised up quite high above the soundboard. And so this allows the player to press down on the strings on one side to increase the tension, or let up to decrease the tension. And so in this way, during the playing of the note, you not only pluck the strings and play the specific notes that the instrument is tuned to, but you can change those continuously by varying the tension. So let's have a look at that one. Okay. So I'll put links to all of those videos below in case you want to see a little bit more. So we could also ask whether it's possible to alter frequencies in a wind instrument by changing the wave speed. And so there it's a little bit harder. Maybe you could, if you want, take a moment to think for yourself whether there's any way that the wave speed might change for a wind instrument. Okay, and so the reason that it's difficult is that the wave speed is just the speed of sound. And so in order to change the frequency by changing the wave speed, then you would have to change the speed of sound somehow. And usually here on Earth, there's a certain pressure of air and the composition of air is the same. And those are the things that determine the speed of sound. Okay. Now there are circumstances where the wave speed does vary a little bit. And so if you want to understand what the speed of sound depends on, it's actually very similar to the wave speed on a string in terms of the quantities that it depends on. So the first one is something like the tension of a string, which remember is the force that is acting along the string. Every part of the string is acting with this force on the next part of the string. And so the analogous thing in air would be the pressure of the air. That determines how much force each chunk of air is exerting on the surrounding chunks of air and on objects. And then the quantity that's similar to the mass per length of the string is the density of air. So that's the mass per volume of air. Okay. And so the pressure on Earth varies a little bit, so that has a small effect on the speed of sound. And the density actually varies a little bit more. And so the main thing that affects the density is the temperature of the air. And so if you think about the air getting hotter, then it turns out that the molecules end up being more spread out if the pressure is fixed, and so it's a little bit less dense. And when the air is colder, it's a little bit more dense. And so either if you have a change in pressure or if you have a change in temperature, then you would get a slightly different speed of sound. But obviously this is not something that you're going to control. It's usually something that's annoying, that's giving you a change in frequencies that you don't want. And so we'll do an example of that in the next question. So I want to point out that one way that you could make a dramatic change in the density of air would be if you were to try to replace the air in your instrument with a different kind of gas. And so you could see various videos. I'll again put a link below where people are switching out the air in their instrument with helium or other kinds of gases that have a significantly different density. Okay. So just to give you an example of a practical situation where you do need to think about the change in wave speed due to a change in the air density, you can think about this question. And so if you want to know specifically how does the temperature affect the density, then if you start with 340 meters per second as the standard speed of sound in air, that's the value for 15 degrees Celsius, and then you increase or decrease the temperature. Basically, by every degree Celsius that you increase the temperature, then the speed of sound goes up by about 0.6 meters per second. Okay, and so maybe just think to yourself now, suppose you were a wind instrument player in a marching band. You warm up inside, it's 20 degrees inside, and then you go out to play in your marching band in the parade maybe, and you want to know, well, what's going to happen to the sound of my instrument if the temperature outside is 0 degrees Celsius. Okay, and here let's assume that the air inside the instrument cools down to the surrounding temperature. Okay, so take a minute to decide which of these is the right possibility, and then I will talk about it. Okay, so we think about this formula relating frequencies to velocities. And now the wavelength of your instrument depends on the length of your instrument and the fingerings. And while it's true that when you heat up or cool down solid materials like the brass that your instrument is made of, it's not a very big effect in this situation compared to the change in the speed of sound. So mostly the change in the frequency is due to the change in the speed of sound. If you forgot about the change in the speed of sound, you might think that the instrument getting cooler would shrink and the frequency would go up. Okay, but actually the speed of sound effect is a much bigger effect here. And so in this case, the question tells us that as you cool things down, the speed of sound decreases. And so according to this formula, assuming the wavelength doesn't change very much, the frequency is going to decrease. So the instrument will play flat. How flat is it going to be? So we could actually quantitatively estimate that as well. And so if you look at a 20-degree change in temperature, that's going to correspond to 20 times 0.6 meters per second change in the speed of sound. So that's 12 meters per second slower for the speed of sound. And in terms of percentage-wise, that's 12 over around 340. So it works out to about 3%. That 20-degree decrease in temperature is a 3% decrease in the wave speed, and that leads to about a 3% decrease in the frequency. And we are going to talk pretty soon about how a semitone, frequencies separated by a semitone, that's about a 6% difference. And so this going from inside to outside, it's about half of a semitone. And so that's a pretty significant effect. Your instruments are not going to be sounding very good if they are playing with other instruments that are not based on sound waves and tubes. Okay. So that's it for this discussion of changing the velocities of your wave, or changing the wave speeds in order to adjust the frequencies. There's kind of one last thing that I wanted to mention before we get into a very different topic. And that is just that there are other kinds of instruments which are not based on stretched strings or tubes. So especially in percussion instruments, you have instruments based on vibrating plates, like a cymbal, or vibrating bars, like in a xylophone, or vibrating membranes, like the skin of this drum. Okay. And the physics of these things is actually pretty much the same basic idea as the way you think about a string or a wind instrument. So for all of these kind of objects, a plate or a bar or a drum skin, like the string or like the air in a tube, there are specific frequencies that these things want to vibrate. In physics, we call these ways that something wants to vibrate with a specific frequency. We call those the normal modes of the object. But it's basically just the same as the examples you've seen. With a string, it likes to do this, or it likes to do this, or I can't do the third one because I don't have 3 hands. Same thing with the head of a drum. So there's a fundamental frequency where the entire drum skin is vibrating up and down. That's the lowest frequency mode of vibration for that drum skin. But then there are many other possible ways that the drum skin can vibrate. It's more complicated because it's a 2-dimensional thing instead of just a string. And so what tends to happen is that you don't just get simple multiples of the fundamental. In this case, you get a bunch of higher frequencies which are not related in a simple way. And that's why most of these percussive instruments, when you play them, there's often some sense of a tone. I'll actually demonstrate that with this is an African style drum called a djembe. And so if I play that one, so there's still some sense of a tone, but it doesn't quite sound as clean of a tone as you'd produce with a trumpet or a guitar or a violin. Okay. And so just to show you that, I've actually recorded this instrument and plotted the spectrum. And so you see that fundamental tone was, I probably tuned it since I made the spectrum. So at the time I played it, it was like 55 hertz. And then you get a bunch of peaks at higher frequencies. Okay. And if you play the instrument in a different way, you get similar frequencies activated, but you see this higher frequency is at a higher amplitude. So I'll just play that second one. So here is the first one. And then the second one sounds like this. Okay, so just depending on how you strike the drum, you can activate different combinations of these various natural frequencies that the drum wants to oscillate with. Okay, so that's it for this segment of the course. And so in the next video, we're going to move on to a rather different topic, which is the topic of sound perception. So we want to start understanding how our bodies actually hear and process sound and music. And this will be important in understanding more why in music we tend to use certain combinations of frequencies in chords or intervals or scales. So check it out in the next video. And that's it for now.